Okay, so what is the crux of computing? If you look into our undergraduate days to present, okay, the crux of computing, why people are developing new architectures, why people are moving from your 8085 to cloud, because the computing power, the computing capacity. Okay, we are trying to have the computing system which can compute more with a lesser cost. That's it.
And also this
yeah.
About the parallel computing.
Yeah, I'm coming to that part. Yeah, sure, that is there. So what I will say is that the computing capacity with our lower cost and at present lower energy, right, is the target of the entire technology roadmap. Right? Can we crunch more data? Can we run more threads in our system, but with a smaller time and with a lesser energy? Right? Because then we can actually go to bigger problems. Okay, drug design, material search, right? The problems in astrophysics. Okay, so if I look into the compare the classical and the quantum side by side, what we see here is that we all know what is the classical computer. Classical computing data is encoded in terms of bits, which is a sequence of zeros and one. Okay, right? When we go to the quantum computer, right, we tell it's a qubit. Okay, right? It is 0 and 1. There are two specific states where the qubit can exist 0 and 1, but a generic qubit, okay, can store two values. Why? Because a generic qubit in superposition can store two values. One, its probability of getting measured as 0, and one, its probability of getting measured as 1. Okay? So quantized energy is not only two levels in the system. Quantized energy have multiple levels in the system, right? And each of those multiple levels are either closer to 0 or either closer to 1. Any of the intermediate energy level can be defined as a component of 0 to be measured as 0 or a component to be measured as 1, and that is the single qubit superposition. So what I just now said, if you try to again absorb that, it means that a single qubit can store two values. One is probability of getting measured as 0 and one is probability of getting measured as 1. Now if you go for two qubits, okay, right, it's a tensor of two values, so it becomes 4. Right? If you go for 3 qubits, it's a tensor of tensor of all these three, so it becomes 8. So ideally, an n qubit system can store 2 to the power n values, right? And so an n qubit can generate a distribution of 2 to the power n, right? And that's the power of quantum computer, right? And now if you operate on the n qubits, you are actually not operating on n samples. You're operating on 2 to the power n samples, right? And that's why in the classical, if you have n bit of storage, n bit of pipeline, right, you can process n bits of data, right? In quantum, if you have n bit of pipeline, n bit of storage, you can process 2 to the power n data, right? And that's why the capacity of computing is exponential in quantum, and that's where the target is, okay? But as we know that though it is, so if you are increasing the number of qubits in the system, okay, then we will have more and more exponential computing power. But there is a sort of thing we have to also take into consideration. More and more qubits we pack into the system. As the qubits are the subatomic states of matter, they interact very strong. In any system, the most finest state interacts more, and the most most bulky state interacts less. Okay, so in that state of matter, there is a lot of interactions, and these interactions will make your distribution a little bit changed than what you logically try to get. And that's why that part is called the noise part in quantum computing. So there is a fallacy that we want to get more larger distributions, we require more qubits, but more qubits will generate more errors, which will generate perturbations in the distribution, and that is why the error correction and error control is so important in the quantum state. Okay, right? A lot of techniques have been devised, and we are very hopeful that at least 100 good qubits, and in a distributed way, 5,000 qubits is achievable in the next 3 to 4 years. Okay, right? And the last part is that that means it's not a thumb rule that every every computing problem is machine learning. Okay, what all the students gets into and comes that, sir, I want to do a computing, okay, what do you want to do? I want to do machine learning. So there is a standard mindset now that every computing is machine learning, which is not. Okay, similarly, every computing will not be quantum computing. Okay, it will be a sort of an accelerator. It will be just like a GPU accelerator. Okay, like every problem you cannot crunch with GPU. GPU will not be useful for every problem. Similarly, the QPU will not be for every problem. So you have to find out which are the good problems. Okay. So the last I will just try to. I think the closing time has come. So last I will say that the technology is pretty good. Okay, we are having a lot of technologies, right? We are having the technologies like the optical photons, which is the first people demonstrated the state of quantum by the polarization of the optical photons, okay? It was the first demonstration, but we know that optical is costly. Optical is not scalable, okay? So people moved into the different types of fabrication-based quantums. We started from superconducting, okay, then ion trap, okay, then Intel is working on electron spins, okay? So a lot of big, yeah, fine. Okay, so a lot of big things, a lot of companies are investing their, labs are investing their money and their effort in this particular thing, and India under National Quantum Mission is also not very far, okay? So I will just keep a bit and I will just tell that what are the, lot of things are there, but I will just keep a bit, and this is something which is very interesting, where the interest of the people of AI and the people of quantum, what together can do. We have found out lot of applications in quantum machine learning. Maybe in another session I will try to discuss what is quantum ML. Okay, but this is very interesting. And also there are something called communication. Okay, a communication rather than quantum computing, quantum communication is a very stable, because quantum communication doesn't require so many qubits as we require in the quantum computing. So quantum communication using QKD, right, is already a technology, and quantum internet protocols are coming up. Okay. Okay, so this is all, and we have a lot of things are there, right? You can just go status of quantum computing. These are the IBM machines. You can look into the net. These are the lot of companies have invested in quantum computing, various avenues of quantum computing. This is the quantum value chain. Anybody wants to look into the quantum value chain and discuss, we have found out this is the quantum value chain, which are interesting, very interesting for business and to shape up the roadmap for investments. I think a lot of business are there. This is the direction what IBM has said. I'm just browsing to very quickly. Okay, exascale computing through quantum computing. This is one of the good thing what we have done. We are the first research group in India to get the IBM Researchers Access Award in 2021. Okay. This is our group, fantastic group, and we have lot of all the good point is that all the students doing PhD in quantum computing in my group is all getting into industry. Okay, name any industry, HCL, Atos, okay, TCS, PwC, okay, LTI, Mindtree, TCG Crest, all are getting into this. Okay, so thank you all. Okay, a lot of research papers we have done over the days. Okay, right, and good publications, and thank you all for listening.